Welcome everyone to another of our Software Design Tech Talks. The series is hosted by SWEdu, the Google School of Software Engineering. Today, I'm very pleased to be welcoming back Titus Winters. Titus was a Googler from 2010 until late last year. During his time at Google, he had a tremendous impact on engineering practices at Google, including around C++, tech debt, testing, and culture. And he was one of the editors of the book, Software Engineering at Google. He was also one of two main instructors for the class we're now calling SWEdu Seminar, where we discussed both testing and design topics, which was part of the inspiration for this talk today. Last fall, Titus left Google for Adobe, where he's now a senior principal scientist working on developer experience. So while I'm sad he's no longer a Googler, I'm really glad we could bring him in to share these ideas with us today. So with that, I'll turn it over to Titus for his talk on design is testability.
Thank you so much, Jonathan. So there's a famous quote from Donald Knuth. "Beware of bugs in the above code. I have only proved it correct, not tried it." This is usually good for a chuckle, but over time I have found that that chuckle might be more nervous than actually amused. As much as I think it was probably a throwaway line for Knuth, it does actually speak to one of the essential dichotomies in tech. That is, when we aim to develop something new or change an existing system, do we think real hard, seek the proper design, find a mathematical or logical or combinatorial proof that our code is correct, or throw some code together and see if it works? That argument, or that approach, argues exploration, experimentation, and hands-on experience tell us whether our software is actually doing what we want. There is, of course, a third option mentioned here for completeness, which is just move fast and break things. Throw it at the wall and see what sticks. Zuckerberg presented this initially, but we know with the benefit of time and hindsight, this doesn't work at all. And even Facebook has walked this back substantially for infrastructure groups. In the end, we need to mostly not be breaking things except in unusual environments because we're grown-ups, right? Like, we're doing this professionally. As to that theory versus practice dichotomy, I see echoes of this in so many aspects of technology today. Thinking and proving and understanding is tied to a sort of academic approach, to theory of computing, to software design, to out-of-fashion but still valuable notions of software architecture. While the experimentation and evidence approach is far more reminiscent of the more robust parts of industry practice, prototyping, experimentation, automated testing. Hooray for having unit tests. Y'all are doing good. There is clearly a spectrum here, right? Few real-world problems are handled only by thinking. And very few useful systems exist where we only understand it through experience, but no theory building. Different companies, different teams, even different people are going to have preferences or biases on this spectrum. But there's a lot of ways to be effective across it. For example, I spent the last 2 or 3 years of my 13-year stint here working with George Fairbanks. Hi, George. Good to see you. George has spent his career in software design and architecture. He's been the editor of the IEEE software columns on the topic. He published a lovely book, Just Enough Software Architecture, and he's worked with countless engineering and design scholars, Mary Shaw, Michael Jackson, people that I respect, and I'm kind of jealous that George gets to hang out with. Both George and I have an instinct that there are some fundamental lessons in software engineering that we think are missing for a lot of engineers. And going into that collaboration with him and coming myself from the testing suffices sort of side of things, I was a little skeptical initially of George's more academic ideas and the idea that you could teach design or architecture in a useful fashion. Instead, over the last couple of years, we found that this dichotomy is much less us versus them and much more two sides of the same coin. I've started to think about this in the same way that I think about introductory calculus and physics complementing each other. Calc might seem a little abstract and irrelevant on its own, but physics, especially like Newtonian mechanics without calculus, seems unintuitive and arbitrary, right? Where does this 1/2 come from, right? It's a list of disconnected laws and equations that you just have to memorize a bunch of special cases for. But if you put these two spaces together, physics and calculus, the explanatory power of calculus combines brilliantly with our tangible, relatable real-world experiences of mechanics in a way that explains the practical and exemplifies the theoretical. And I would argue, and I think George agrees, that the same is true for design and testing. So here's my favorite example. Imagine we have an API, piece of software that we want to test. And I'm not going to specify exactly what it is. It could be a function, a class, a microservice, maybe a whole program. What is enough testing for this? Until working with George, the best I had was, I'll know it when I see it. But there have been at least a few guideposts over the years. Right? Many people, especially the security conscious, will tell you that if you're handling untrusted inputs, you should use a fuzzer, and we'll cover that soon. Any of us with formal math or logic background know that proof by example is not proof. And we could probably go on, but these two endpoints, the heavyweight machinery for complex systems, fuzzing and all of that, and just the reminder that a single example doesn't actually cut it is sufficient for now. So let's think about design. I want to pause here and reach into George's software design terminology. I want to talk for a moment about control. This is a tangent, but it's a useful one, I promise. Imagine you're working with a software system and you need to make a change. The argument here is there's roughly 3 scenarios that you can be in with respect to that system and your ability to make change safely. In the worst case, you have no control at all. Making any change to the system comes with great fear. You don't know what's going to actually happen, nor do you have a good way of figuring it out, short of just trying it live in front of the world and everyone to see, right? With all the commensurate risks that come with that. If you're in this scenario, you have a lot of work ahead of you. There is no room for fear in engineering. Like SREs say, no haunted graveyards. If you have systems where nobody is willing to touch it because they are afraid of what is going to happen, it is imperative that you go in there and bust them ghosts. Over time, all software has to change. And if you cannot find a way to do that safely, then you are making an awfully risky bet that the scary stuff dies off on its own before you are forced to change it. And if that forced change comes during an outage or a security incident, you're going to have a really bad time, y'all. In the slightly better case, you might have statistical control. I think this is where a lot of Google teams are. There are tests, there are test environments, there are experiments that you can run to figure out, is it likely the case that this change is safe to make, right? You may wind up spending some time, likely a substantial amount of computing resources, but you build up statistical evidence of safety and correctness. And in the end, you can hopefully be pretty calm about the next release or rollout. This is where the majority of successful large modern software systems tend to sit. Through a combination of manual and automated testing, hopefully much more automated, we build up that evidence to convince ourselves that what we are doing is safe, even if we don't necessarily consciously understand the full ramifications of all of it. And we certainly won't be able to prove that it is safe. This is unsatisfying for a lot of people, but it is an important theme. Beyond a certain point, additional levels of proof and certainty and redundancy become substantially more expensive, right? Talk to any SREs, right? How much does it cost you to get 1 more 9, right? It turns out that being 99-point-something% sure is often hugely cheaper than being 100% sure, right? This is why proof of correctness is fairly rare in software, right? The difference is usually lost in the noise. In the rare best case, speaking of control, we might call it intellectual control. This is the state where you and hopefully the team around you fundamentally understand what the software is doing, how it works, what parts depend on what parts, and you can reason through from first principle understanding the ramifications of any proposed change. This is wonderful, but also doesn't scale at all, right? As an example, if you need to make broad changes, the large scale changes team is sitting here in the front. Without any sort of statistical control, you're left manually tracking down who understands every individual software component and asking them, is it okay for me to make this change? And you can certainly see at Google scale, that ain't gonna work, right? We'd probably have to have both. SC and IC, statistical control and intellectual control, are slightly orthogonal, and both are good. With that vocabulary in mind, let's go back to our quick and easy testing guideposts. Here's a very easy function, and I'm doing this in Python so that we don't have to worry about sharp corners. Note, there is no integer overflow in Python. If this arithmetic fails because of overflow, Python automatically upgrades the type in question to be arbitrary precision integers. I guarantee you there is nothing hiding behind the curtain. This code is as correct as anything I can present. Okay? Now, we already said, and we already know, proof by example is not proof. But at the same time, with only a couple tests, I get a pretty substantial amount of evidence that my implementation of add1 is working correctly. In fact, I would grade this as at least a B-, right? I have to think a little bit to convince myself that my chosen input in the success case is robust enough to answer most of my questions. And there might be a couple other success cases that would make me feel better about this, like adding 1 to 999999999. But the broader point is, proof by a couple of examples is actually pretty sufficient here. It isn't proof, but it is giving us a lot of experimental understanding, that is, statistical control. So is the lesson that I want you to take away from this that one good example and one error case example is sufficient for all of your tests? No! Let's see how we feel about this when we change from adding 1 to, say, decoding a JPEG. Anyone feel good about these tests? All right, what's the difference fundamentally between adding 1 and decoding a JPEG? It's control. We can look at add1, or more precisely, we look at the specification of what that is trying to do, and we all have a pretty good intellectual control of that problem space. Or at least we should, because we passed kindergarten, right? I'm hand waving over one aspect of that. If the exception handling is bothering anyone else, don't worry about it, I'll get to it. But by comparison, I would argue that no human actually has intellectual control over a JPEG decoder. We can specify what it does very precisely, but that is not remotely the same as actually being able to reason about it in our squishy compute brains, right? So let's look at this another way and go back to the idea from security of untrusted inputs. Right? Modern secure coding guidance will generally tell us if you're handling untrusted inputs, you should be very careful or you should use an advanced testing tool like a fuzzer. And in most discussions of the problem area, we would just call every JPEG untrusted and move on with life. But I think the idea of control is actually more illustrative. So let's take a look at add1 again. If I make my add1 function callable by random users on the internet, how much should I be worrying? Do I need to randomly generate 1 billion inputs for add1 before I'm comfortable exposing this function to the internet? Or do I exhaustively iterate through all integers? Does anyone think that this is a good use of compute time or resources? On the other hand, if I make decode JPEG callable on the internet, anyone got concerns? Yes, of course, we absolutely do, right? Which is to say, it is not actually just about trusted or untrusted inputs. It might not even be primarily about that. It's about how much intellectual control we have over the functionality and the input to a given function. So popping up the stack a level, with the ideas of statistical and intellectual control in place, we could look at the question, what is enough testing for this API? And do a little bit better than I'll know it when I see it. If we have IC over the software and its inputs, well-chosen unit tests, that is proof by example, is actually sufficient. In fact, had Knuth coded up the priority deck that he was writing about and run even 1 or 2 basic tests, I think most of us would take that as pretty solid evidence that the class actually worked, both in theory and in practice. If, however, we lack intellectual control over either the software or its inputs, we need something stronger? Fuzzing question mark? This is still not entirely satisfying, but it's an improvement over I know it when I see it. If we go back to software design concepts and vocabulary, there are other ideas we can leverage. In particular, let's touch on design by contract. DBC is an idea that dates back to the late 80s and the beginning of the object-oriented programming movement. In a nutshell, DBC is about applying some formalism to the behavior of a bit of software. And as with a lot of ideas in the 80s and 90s, some proponents were a little zealous about the approach, requiring very formal specifications are produced for absolutely every function and type and everything that you could imagine. Personally, my suspicion is that the basic ideas of DBC are actually critical for software engineers, but we need to be a little judicious in where and how we spend their time to bring out the formalism. Sometimes things are actually obvious, and even when they're not obvious, they might not need to be presented with that sort of formality. The essential point is that we've thought about and documented the behaviors of an interface. So let's return to add1 and look at the doc comment that I added here. In DBC terms, given is what we would call a precondition. This is a property of the input or the program state that must hold when this function is being called. So long as that precondition holds, return or other descriptions or other side effects are what we would use to describe the post condition. What properties are guaranteed to be true once this function is done, right, has left the stack. Now, in this case, I would argue that the precondition here is incomplete. Specification doesn't cover all the values, even for just the types that are implied by this function. What happens if we are handed a string whose value is not a well-formed non-negative base 10 encoded integer? In our tests, we assumed that throwing value error was the correct behavior, but strictly speaking, the contract doesn't say anything about that. Maybe we should be throwing value error. Maybe we should just return 0. That's a terrible idea. Don't do that. Maybe we should abort. Who knows, right? If we want to be good API designers, we should probably aim for total coverage of the preconditions. For the types accepted by our API, there is exactly one precondition or set of preconditions that fully describes each possible value. And that might lead us to something to add to our .comment contract, throw value error for any other type. Now we see that add1 has two separate behaviors, the nominal case as well as an error case. These are like sub-clauses in your contract. In order to be reasonably tested, we obviously need at least one unit test for each behavior. So we can update our testing guidance accordingly. Now it's for each behavior in the contract. If you have IC, proof by example suffices, and if you lack IC, we'll do something else. And this feels a little bit better to me, right? Because it's not actually just IC over the API and its entirety, it's behavior by behavior, right? Everyone in this room, I suspect, can reason about the simplest error handling cases for decoding a JPEG, even if you can't mentally reason about the nominal success case, right? If the contract for decode JPEG says you have to hand me a buffer for decoding, and you handed me a integer, right? Like I can work out what the error handling is supposed to be in that case, right? So going back to add1 and our tests, hey, we have a bug here, right? Now, as specified, -2 ought to throw value error, but it currently returns -1, right? We over implemented, right? And this highlights one of my favorite points of tying design and testing and DBC into our test plans. Even in relatively simple scenarios, there's a three-way consensus running here. All three of the implementation, the contract, and the tests need to agree. If any of them don't, there's a bug somewhere. Maybe you specified the wrong thing. Maybe your contract isn't saying the thing that you wanted it to. Maybe you implemented the wrong thing, and that's just sort of a normal bug. Or maybe the tests are fundamentally wrong, right? In this particular case, we have two options. We can fix the implementation, which would make it harder and slower, harder to implement for relatively little value, or we can tidy up the contract. So I'm going to do that. When trying to specify the contract for adding one and handling negatives, we have two options. We can define the behavior to match what positive numbers do, which is very easy for this implementation. Or we can do a thing that original DBC purists might hate, but in practice is fairly common in computing, which is we leave it undefined. If the rules in DBC are effectively for a given invocation of this function, if exactly one set of preconditions captures the input state, the associated postcondition or postconditions must hold after the function executes. If no precondition describes this invocation, there is no associated postcondition. That means any behavior is allowable. We haven't constrained it in any way. There are two critical things to realize about this because this is about to get scary and weird. Software systems with partial contracts and undefined behaviors are far harder to use well or safely. I know an awful lot of C++, and it is riddled with undefined behavior. The C++ community just refers to it by shorthand as UB because it is such a common term. By comparison, a higher level language like Python has vastly less UB. You really have to try to even pretend to get into a state where the Python interpreter isn't trying to tell you what the correct answer is, right? It doesn't have a definition of correctness. That said, implementations of systems that leave UB in place can be more efficient. consider a minor variation on add1, but now in C++. And weirdly, I'm not changing languages here because I want C++'s UB, changing languages here because I need strings to be mutable if we want to do carry the one in place, and Python string immutability ruins the whole example. So here, I'm making the problem a bit more complex by assume the input may be up to 10,000 digits long, right? This is still arguably the earliest and simplest algorithm that any of us ever learned. This is carry the one, right? And I guarantee you, it's not even carry the two, right? This is carry the one. But because we're allowing for inputs up to 10 to the 10,000th, substantially larger than the number of particles in the universe, the simple answer of converting to int or 64-bit int or anything doesn't work. And further, by doing the work in place, we can avoid doing order n work in most cases. Only in the case of a string of all nines do we even look at all of the input data. So the average case, if you work out the math, assuming a uniformly distributed input, is order 1, right? You're going to do on average 1.1111 cycles through this loop. So here, this I think is a great example of the complete versus partial contract issue. If we add for invalid inputs, throw an exception or return an error, that means that we have to look at all of the input, potentially all n digits, before we find something that was an error. If we leave the contract only partially specified, the average case drops from order n to order 1, and there are going to be times where that matters. We see echoes of this trade-off all the time, from high-level API design to programming language design. Tons of stuff in C++'s UB, specifically because it is too expensive at compile time or link time or runtime or any combination of those to diagnose and prevent your bad program behavior. Use after free memory safety bugs, it's UB, because retrofitting memory safety into C and C++ would invalidate tons of old code and add runtime overhead that the industry is not willing to pay for. Type punning, that is interpreting a sequence of bits in memory as a different type than you actually wrote it as, that's UB, because once you have an object model and object lifetimes in C++, it's not just a bit pattern, right? We need to know that the object was constructed and destructed, right? You have to actually call constructors. You can't just reinterpret memory however you want. And the compiler is allowed, in fact encouraged, to give you all sorts of grief when you mess that up, right? ODR violations are UB because compile and link time operations don't have enough information or compute time to prove that you didn't violate the one definition rule. C++ fundamentally defines only the behavior of well-specified code and leaves tons of pits full of spikes just on the other side of that specification. And the most surprising side effect of this is, since there is UB in your program at compile time, there are inputs to a C++ compiler that will generate a binary, but that is not formally a program. The behavior cannot be defined by the language standard. Another way to say that is there are false positives in our basic notion of, is this a program? And that is entirely due to this specification versus efficiency trade-off, right? In theory, UB can do anything. There is no post condition to satisfy. Any behavior at all is allowable. There was a page, might still be a page, which I did not write, here in Tip of the Week Labs, I think, that says if you have UB in your program, it's allowable for your program to email Titus to say that you are a bad programmer. That is technically true and theoretically possible. In practice, the most likely result that you're going to get is a crash. Hopefully it's an immediate crash, but again, anything is possible. It might crash at some arbitrary point in the future, right? C++ does not make any of these things easy for you. So what do we do when we have a really complicated API beyond our level of intellectual control, but we want to achieve a reasonable level of statistical control, especially while we have to worry about things like undefined behavior in our programming language? First off, since it's undefined, we can implement it to do whatever it is that we want. There is no valid program that relies on that behavior. And this turns out to be very handy. Advanced tools in dynamic analysis, things like the sanitizers in Clang, ASAN, TSAN, etc., rely on exactly this trick. We can modify the compiler to diagnose when we are doing something that is undefined, say accessing memory that we're not currently allowed to, And then we can do whatever we want, especially including aborting the program and logging a bunch of diagnostic information so you can track down what happened. All right. If you do this effectively and you tie it into the compiler in the right ways, overhead tends to range from 10% to maybe 2 to 3x. So you're probably not going to deploy software to production with that instrumentation, but you can at least run canaries and tests with it. But let's look at our work in progress for how do I test this API? If we lack intellectual control, we need something stronger, right? If we lack IC on the software, the API that we are testing, dynamic analysis could work. If we lack IC on the input, selecting a couple easy test cases isn't necessarily going to tickle all of the important bugs. And dynamic analysis does not prove a lack of UB. It argues very strongly a lack of UB in the code that was actually executed in the way that it was actually executed with the inputs provided. So if we don't have powerful ways to generate inputs, we aren't really even going to get statistical control on the hard cases like decode JPEG. Feeding one picture of a cat into your JPEG decoder doesn't actually tell you that the thing is actually under control, right? This is where fuzzers come in. I said I'd get there. Fuzzing also dates back to the late 80s and is roughly randomly generate inputs and just hammer on this thing and see if it crashes. Remember, crashing is a common subset of your possible behavior when you trigger UB. Modern fuzzers take ideas from symbolic execution, dynamic analysis, program analysis, and all sorts of other things in order to aggressively find new execution paths through the code under test. In particular, I really love coverage-guided fuzzing. By working with the compiler and the operating system, you can monitor which paths of ifs and loops and et cetera through your code have been executed. And with a little bit of logic, you can generate inputs that will trigger as many distinct code paths as possible. Coverage-guided fuzzing combined with dynamic analysis tools like the sanitizers is an incredibly potent recipe for getting a lot of statistical control for a complicated API like decode JPEG. One of my favorite demos of all time is this one, CPPCon 2015, Kostya, who's a Googler here, doing a live demo of a coverage-guided fuzzer with address sanitizer, trying to find 2014's Heartbleed bug. For those of you that weren't around in 2014 or weren't paying attention or forgot, that was 10 years ago, this was a very severe issue in OpenSSL. If I remember correctly, this was if you send some bad inputs to an SSL endpoint, could allow you to read the private keys out of that endpoint and totally obviate all of the encryption. It's caused a widespread industry panic as the majority of the software on the internet had to be patched and updated over the weekend. In this 2015 talk, Kostya shows this type of fuzzing, coverage-guided fuzzing with sanitizers, hooked up to the OpenSSL packet processing interface, and it finds the Heartbleed bug in about 10 seconds on a 2015 era laptop. This is not proof of correctness, but this is demonstrating that fuzzing does provide a powerful amount of statistical control. Or at least mostly, right? It's a powerful amount of statistical control against crashes and other forms of undefined behavior in the language itself. Fuzzing for higher level languages like Python or Java might trigger crashes in a few places, but that's pretty rare. In most cases, we're left with, was there an uncaught exception? And that's not exactly the same problem or severity, right? It's one thing to have machinery that handles, did we do something actually fully undefined? And it's a much different thing to say, is this working as intended, right? For that, we need to evolve fuzzing, Pokemon style, into its next form, property-based testing. Property-based testing is to well-specified contracts what fuzzing is to undefined behavior. It's maybe not a perfect analogy, but it starts to get us there. Property testing takes the ideas from fuzzing, the generation of random inputs, and says, hey, maybe we should look at the result of the computation instead of just, did you crash, right? So here's an example from the Google Fuzz test system, which ties in very nicely with Google test. This test says effectively, run coverage-guided fuzzing on the input variable I. Rather than sending in totally random values, we're going to match the contract of my API, which is saying, which we believe is saying, return true if given a positive input. So the domain here of that behavior is limited to positive inputs. For each such input, the call to my API will return true, right? And we just expect that the test fails if that fails. And additionally, since this is running in the same infrastructure as all of our sanitizer instrumented coverage-based fuzzing, if any inputs happen to trigger the types of UB that would be a problem, we still get good diagnostics for that. So what can we say about the behavior of my API on inputs that aren't positive? For that, we would have to go look at the contract, at least as far as any logical assertions go. But another thing that we can do is just add a second fuzz test with no assertions, because property-based testing devolves into fuzz testing in the null case. Since this is still a coverage-guided fuzzer under the hood and we're still using sanitizers, you at least are checking for the language level UB. It's not testing any properties of the function at this point, but we at least ensure that calling this doesn't make things worse. This gets to the broader point about property-based testing, which is it's not quite as easy to apply as fuzzing. We need to be able to express some property of the output based on a completely random input. In cases like, hey, I will return true for all positive integers, there's a clear thing you can test. But for something like decode a JPEG, if I feed you a random JPEG, even if I guarantee that it's a valid one, what sort of assertions do you make about the resulting bitmap after it's been decoded, right? We know that it's an image, but we let the random generation specify dimensions and colors and content. How do you assert anything about the results of that decoding? In the degenerate case, property-based testing, if you just said, we're going to do property-based testing for everything, you're going to wind up implementing everything twice, right? Once for your tests and once for your actual production. And that's a lot of work that we're just not going to do. But there are specific cases that do much better. There's a blog post by a guy, Scott Woloshin, who has a very nice write-up on the types of properties that you might be able to exploit with this approach, depending on the contract of the API in question. If you have different paths but the same destination, if you have commutative operations, that is, try asking the property framework for multiple inputs and apply those in different orders, right? If my API of X and Y is supposed to be commutative, demonstrate that it's commutative, right? Call it with A comma B as well as B comma A. If you're implementing an operation and its inverse, then test that a random input will round trip. This works for encode, decode, encrypt, decrypt, serialize, deserialize. There are a lot of those pairs out there. Given an input or an operation on existing state, are there other invariant properties, right? If you filter a collection of objects, the resulting collection should certainly not be larger. If you apply a map transformation, the resulting collection should be the same size. If you modify a single element of a collection, the others should not be modified. If you modify one property of class person, the other properties should not be changed. You get the idea. On data structures, this might also work for things like arity and sort order. If you insert n distinct elements into a set, you should get those same elements back. And if the set happens to guarantee sorting, you should be able to iterate through them in sorted order as well. If your operation is idempotent, you might be able to test that. If applying the operation more than once is guaranteed to return the same result as doing it the first time, that is easy and maybe even valuable to validate. Sometimes you have hard to prove but easy to verify. If you're implementing a very complicated algorithm, it still may have an easy to verify answer. Prime factorization is a clear, obvious example. Doing the factorization is hard, but checking the answer is easy. You could also imagine using this approach to test a randomly generated maze. I certainly do not know how to generate a random maze off the top of my head. I've seen the algorithm, but I know that running breadth first search will solve it, and I can do breadth first search in my sleep. And if you do happen to have two versions of the same algorithm, this isn't a very easy case, right? While that might seem wasteful in the general case, it does come up. Maybe you're doing a rewrite for efficiency, or maybe you're doing a clean room implementation of a component, or maybe you're swapping out lower level infrastructure and you're asserting properties of a higher level component that don't change depending on which lower level piece you're swapping out, right? Now, it's certainly not the case that every API that we could be implementing is suitable to any of these. But I will assert that in a well-structured project, you're going to find a higher density of utility functions and classes that could be validated in this way. Because time and again, we find that testability is strongly correlated with good design. If you can't test it, you probably didn't design with the right abstractions in mind, and vice versa. So now with a proper understanding of dynamic analysis, fuzzing, and property-based testing, we can fill in our gaps a little bit more. For each behavior in the contract, again, if we have IC, just proof by example is fine. If we lack IC, we need stronger evidence, fuzzing, or property-based testing, depending on if we have good properties to actually test. When it comes to testing what is computed, this little flowchart actually covers an absolutely huge swath of the problem space, in my experience. But that's still not quite the whole story, because sometimes it's not just a matter of getting the right answer. It's also a matter of how did we get there? And that brings us to one last intersection between design and testing, and one last piece of borrowed vocabulary. In the design literature, getting the right answer is due to getting the right functional attributes, right? That's the basic computational correctness, right? Sometimes we care about other things: security, latency, scalability, readability, reliability. The shorthand is often the ilities. And there's two most common terms for this counterpart to functional attributes: non-functional attributes or quality attributes. I personally much prefer quality attributes because non-functional sounds like broken. It's one thing to say, here's decode JPEG, it decodes a JPEG. And it's another thing to say, here's decode JPEG, it's expected to return in under 100 milliseconds, it consumes a bounded amount of memory, and it will not crash on even malicious inputs. For the sake of discussion, I'll focus on latency as our exemplar quality attribute. If you want to test whether decoding actually returns in under 100 milliseconds, how do we test that? I think we certainly have intellectual control over that property, right? We know how to measure the passage of time. We know what 100 milliseconds is. We hopefully even know what normal inputs for that decoding benchmark would look like. So we run one test and a representative input and see how long it takes. I don't think anyone's actually going to be convinced by running that one time. I know I certainly wouldn't be. If you want to get a sense of how long something takes to compute, we kind of all know you need to run it a few times. And even there's some substantial question marks on that result. Sure, you don't need me to say it out loud, but computers are complicated, y'all. There's cache effects, NUMA nodes, processor scaling behaviors, virtualization, optimizing compilers. All of these can and do have meaningful effects on processing speeds and thus latency and benchmarking results. The best we can really say for testing quality attributes like latency is that it requires an empirical approach, experimentation. And the more that the system under test matches all of the sort of abstract properties of how we will use this code in production, the more we can believe the results, right? So we need representative hardware, build configurations, inputs, load on the machine in terms of other jobs, those types of things. There's a host of issues to pick apart when really getting into the difference in handling for quality attributes versus functional ones, far more than I have time in this talk. But I'll summarize with one more George quote on this matter. Functionality is localized, quality is diffuse. That is, we can ask where the login code is. You can't ask where the security code is. It's a matter of everything not being insecure. You can ask where the JPEG decoder is. You can't ask where the performance code is. It's a matter of not letting anything be slow and wasteful. It's one of my favorite insights of the past year or so. Even when we have a good sense of how to write good code and how to test it, if you really need your aggregate system to exhibit any given quality attribute, say good performance, good resource usage, we have to be diligent everywhere. And that is hard. So pick your quality attributes wisely. And you want to not overdo that because you are not going to be able to afford to go hog wild. And this leads me to one final tangent. In the last few years, I have spent a lot of time thinking and writing and speaking on the software workflow. And so much of the workflow is fundamentally about functional attributes and functional defect reduction, right? We write unit tests and configure our CI systems like TAP to manage basic functional correctness. We get some very generous timeouts on those things, mostly to catch cases where a test is deadlocked. But most of the time, our CI system and test framework are not going to notice minor regressions in performance. And that reinforces the idea that we have to rely on empiricism. It is a matter of tracking state and differences in moving averages rather than responding on a single bogus sample. But if most of our workflow is about catching regressions in functionality rather than quality, What do we have that actually monitors quality? Sometimes we can build tools for a couple limited qualities that we care about, benchmarks or auto formatters. But in the end, the primary human activity in the workflow is either pair programming or code review. It's the only time when another human is looking at our code and we really have someone to answer to on issues of quality. Hey, is this sufficiently documented? Is that computation wasteful? Is there a better algorithm? Is this implementation overly clever? These are human matters. These are quality matters. And that gets to the heart of a lot of issues around code review. Sometimes it feels nitpicky or unimportant, but that is a slippery slope to give up on, because if you don't have any other safeties in place to hold the line on quality, you're going to have a bad time, right? One of the things that I've increasingly come to recommend to groups, like for whatever your product is, write out what your quality targets are. What are the quality attributes that matter to you? And don't write them out as all of these things matter. Put them in a priority list, right? I prefer this even over those, right? Write it down. Get the team to agree to it, right? Point at that when you are bringing it up in code review, because you cannot let that slippery slope dominate. Otherwise, you are going to fail on quality. And that quality attribute discussion leaves us with one final modification to our testing flowchart. If it is a quality attribute, you're going to have to take an empirical approach, right? Many samples, right? Run a bunch of experiments, track things over time. It's a different set of processes than just basic CI. Okay? Otherwise, the rest of the flowchart applies. Before working with George and before having specifically these vocabulary ideas from design, questions like, what is enough testing, or how do I test this API, were annoyingly squishy. I could give a couple specific examples, but never anything that felt remotely objective. With the ideas in place of intellectual control, design by contract, and quality and functional attributes, it became a lot easier to discuss the APIs in question, the problem complexity, and make it much more straightforward, although certainly not entirely objective or mechanical, to judge what is an appropriate level of testing. Modern testing practices like property-based testing and coverage-guided fuzzing are incredibly powerful, but without these design ideas, I think it's almost impossible to reliably know where they are worth applying. Discussions and problem-solving exercises like this have really highlighted the deep connections between software design and software testing. I said at the beginning of this talk, it's really easy to dismiss design as being entirely abstract or impractical, but when we see it as a vehicle for explaining practical concerns, like how do I test, the utility becomes a lot more obvious. And the reverse is true. Testing is terribly powerful. Continuous integration systems, unit test practices, all of those things are responsible for keeping massive old projects not only functional, but malleable enough to change over time. But it is one thing to have tests, and it is a far different thing to test well. The past few years have convinced me of one thing above all. It's hard to have a good understanding of testing without drawing on the critical ideas and lessons and vocabulary from software design. I, for one, think that these are really two sides of the same thing, the calculus and physics of day-to-day software engineering. Thank you.
Thank you, Titus. Very much appreciate that. I like the idea of stack ranking quality attributes for a code base. Is there a list of common quality attributes?
George or Jonathan? I mean, we could all probably brainstorm a reasonable list of like most common 10 or something, but I don't know that there's an official thing.
There's nothing.
I think,
you go to Wikipedia, there's a reasonable list, and also there's a 1995 Software Engineering Institute tech report by this guy Barbieri, I think is his name. Anyway, I'm sure using your favorite search engine, you could find one of those. But mostly those are useful for just expanding your brain, you know, to like improve your imagination for like, oh yeah, I care about that too, rather than it being some sort of official taxonomy that you need to adhere to, right? It's in fact, in one of the software architecture books, they had a client, a customer, or a company that was in Iowa, and they had a hard time recruiting engineers to come to Iowa. So they decided that one of the things the system had to have was Iowa ability, which means being technically interesting enough that they could recruit people to come to Iowa. Okay, so point being is the quality attributes are anything beyond, you know, the what you can get feature-wise, functionality-wise, and don't be constrained by a taxonomy.
Yeah, I like that.
No. Yeah, I'll just add to that real quick. Two internal resources you can pull for as well. I mean, there's Go Architecture. We probably have some things listed there, but also Blue Doc, like George was talking about, like kind of using things as a checklist. Blue Doc, someone is intended to be that kind of checklist. Like, oh yeah, I didn't think about accessibility in this particular product. I should think about that quality attribute too. Anyway, we'll take some live questions. Dimitri, go ahead.
Thank you. The quote, quality is diffuse. I find diffuse to be a very vague word. Can you better clarify what's meant by that word?
I mean, it's everything. It's ambient. It's nebulized. Like, I don't think that's a better word. It is the matter of nothing in your program that matters violates the quality attributes that you're trying for. And it can't be localized to one component, right? If, like, going back to the security example, right? You can point to where authentication or identity code happens, right? But that's not the same as nothing here is insecure, right? Like, a particular piece of functionality exists in a localized place, but equality is an emergent property of the whole program. And that's harder because that means that we have to maintain that ourselves through diligence. And that just feels like being kind of nitpicky if you're not really explicit with your team about this is a thing that matters to us. Does that make sense?
Yes, thank you.
So I've spent most of my time at Google working on search. And in search, we have these giant binaries like superroot and gwist that is laughable to even think about having intellectual control over all of one.
Yep.
For superroot in particular, there was an initiative at one point to try to split it up, probably more than one point, and they gave up for reasons that I don't actually know. Basically, my question is, do you think we should try hard to make our systems small enough that we can understand them? Or do you think this is sort of like an inevitable cost of building something like web search?
I think it's probably inevitable. Like, it's a thing that I've said for a lot of years now, which is everything interesting in our field is just barely possible, right? Like, because fundamentally, everything that's substantially easier than possible, we've probably already automated, right? There's already infrastructure for it, right? And everything that's impossible, we fail at, right? So the only interesting stuff in software is the stuff that you can just barely do, which is why I have a job telling people to be better at, like, pay attention to the basics, right? It's all actually about buttressing so that you can lean out further over that edge of complexity, the complexity chasm, right? But the stuff that's like, okay, this is the first time humans have ever done something that complicated, I would be aghast if we ever managed to actually keep intellectual control on a thing like that. So, like, search, I think that's unfortunately going to be the nature of the beast, right? And that's not to say be okay with it, right? The more that you can carve out regions of intellectual control and maintain that and hold the line, the better off you're going to be. But, like, yeah, I think it is inherent.
That makes sense. Thanks.
Yeah.
Taking another from the GBC, we've got Venkatesh. Go ahead.
Hey, Titus. Nice to see you back here. My question is more, so DBC is an old topic, 1980s. There have been courses, like graduate courses, undergraduate courses that has covered specifications and such in colleges and all. But when you see it in industry, it's not caught up. George offers a DBC course at Google. I'm like, okay, smart set of people, but at Google, all of them, but still DBC is being offered as a course. So it seems to me when I look at this, when somebody looks at this picture, there's a big disconnect between the industry and academia in terms of either property-based testing being earlier available as quick check and Haskell and so on and so forth, or JML and such languages talking about specification-based programming and stuff. So in your experience, both at Google or at Adobe or elsewhere, what do you think is the disconnect between why do you sort of your hypothesis as to why there may have be a disconnect that only now after DBs were introduced in the 80s and a lot of other academic efforts have existed in the last 2 decades that we are now sort of slowly getting to a point and embracing, yes, maybe DBC is good, we should probably take it up. And again, I'm not even sure that we as a community are wholeheartedly embracing it, but there are efforts, that's good to see.
Yeah.
So any thoughts?
So I think it goes back to that idea that the sort of a lot of the older ideas in design just come across as academic and stuffy and inapplicable. And there have been domains, like if you look in programming languages and formal specification, right, we still talk about DBC ideas all the time. So it never went away. And it's kind of, I think some of the bad takes on, oh, Agile means we don't do design, combined with some of the like overzealousness of design will be the right answer. Everything is formal. We prove everything. That was so popular in the 90s, or late 90s and early 2000s. Right? I think those two things kind of together gave a bad taste to a lot of these topics. And I'm thrilled to have had George in my life to like, no, let's go back and look at the ideas and not the like baggage, and reevaluate some of these things and see how those are applicable to the set of problems that we're facing in modern software. George?
I need a 90-minute tech talk so I can be as kind and as generous to the things I've learned from you as you've been here today.
I'll go watch it.
To Venkatesh's point here, when I was in high school, I thought that professional engineers learn calculus in high school and college so that when they get on the job, they can apply calculus. I now don't think of it that way. I think of it as you do those activities to get your brain thinking about engineering problems in a certain way, such that when you're confronted by other kinds of engineering problems, they're not exactly calculus, but your brain is already ready to interpret them in a formal way. What I want out of Google engineers in studying design by contract is to get past it, to get to exactly the kind of presentation that Titus was able to do today, so that when you understand, hey, this contract is fuzzy in this particular way, should I be specifying what happens under error cases? What kind of testing should I be doing? All of those things come out naturally after you wrestle with design by contract or just contracts generally and say, what are these methods supposed to be doing? And you get past all the initial deflections of, everybody understands what that means because I wrote it in the name of the method, and a variety of other excuses that as you go on become less and less convincing to you. So I want everybody to get past that, not to get enthralled with the fussy mechanics of the formalisms, but to understand them so that they can see the truth in the software that they're looking at and get to that point, make good decisions.
Yeah, bravo. Thank you, George. That is a beautiful way to phrase that. I guess it wouldn't be a talk in the mid 2020s without saying AI. But also, if we're ever going to get to a world where I'm tolerant of AI generating our code, you're gonna write contracts, because there's a theme in all of the user experiences for generative AI systems that works, and that's you specify what you want, and then it generates it for you, right? So a workflow that I am okay with is write out the contract. Hey, are these the tests that would go with that? Do that back and forth until you're actually happy with it. Okay, let me generate some code for you. Okay, we'll go back and forth on, okay, and now we have the whole thing, right? That I can imagine being okay with. All of the discussions about I'm going to synthesize your unit tests from your code. There's Hiram's law. We might need to talk, right? There's no way to separate what an intended versus accidental behavior of your function is from the code. Like, if I had any power here, I would have fought to the death to prevent deployment of any AI system that was doing that to Google 3. And the answer here goes back to, you need the vocabulary and ideas and some of the practices, but not the fussiness of design by contract, right? So there's something here.
Titus, just to check, so we got the room till 2:30. You're good to stay that long?
I think so.
Okay,
Yeah,
great.
sure.
Okay. I'll take one from Dory then. Let's see, we have, would time complexity or space complexity be a part of the contract or more of a quality attribute? Is it testable?
Time complexity and space complexity are, it's a little bit fuzzy, but I think they're mostly quality. Joseph has thoughts.
If you've ever done Top Coder, Google Code Jam, anything like those old programming contests, there's a really good way to translate some of these requirements into user visible behaviors that you can test. The easy one being, okay, you have to create this thing and it has to handle an input of this size and finish in this time limit. There's your test. And if you time out, your test fails and you've got a problem. So the only way you can pass that test is if you implement it in a way that can finish in that time frame. So that's a good way to do, say, time complexity. It may be harder to enumerate the cases, and quicksort's the obvious one. When the degenerate case that would actually hit n squared, you need to fit it, give it an input that would be big enough to cause it to time out. So it becomes an interesting question as to how you're going to get that right test case. And that's a case where something that can actually probe it and generate a test case for you would be helpful. Sort of like the way fuzzing and finding code coverage paths to do it would help. But I find it powerful if you can translate what seem to be these kinds of requirements into something that's user impacting. Oh yeah, well, it better handle an input of whatever, product at 2 primes, billion digits each, blah, 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 come back in X milliseconds, whatever. Then you better have a way to solve it. And you can build up to that. So I think beyond that, then like space complexity be a bit harder because then you'd have to be watching how much memory or whatever you'd be needing. So some of it would be trickier because you harder to get that user visible turn on it. But if you can, then it's testable.
Yeah, and it's not that quality attributes aren't testable. It's that there's not always an obvious way to make it easily testable, and those tests may or may not be representative. Like, I think the complexity things are, most people are probably going to say it's a quality attribute, but it's a little fuzzy. So, and these are vocabulary. It's not a taxonomy. So, is that okay? I'm going to go with that's okay.
All right. Well, next question. What's your feeling about formal methods, proof, model checking, etc., popularity in industry? Is it gaining any momentum for core critical parts of wider software projects?
Not really. I think that there are a handful of places where it's a really good idea, but I would also say that a lot of the, if you go back into the formal methods, literature back to like the 90s, having a type system came out of formal methods. We adopted that, right? A lot of the things that are high value from formal methods, we don't think of as formal methods anymore. And the stuff that's left is a sometimes food. And it's a really, really good sometimes food. Like if you're writing a, God forbid, lock-free data structure or something, like, yeah, prove that your memory ordering and progress guarantees are working. But most of the time, proof is way more expensive than is actually valid or useful, I think. So that's where I'm at.
Let's see, next question. How do you estimate the cost of a component being out of intellectual control? How do you estimate the cost of bringing a component into intellectual control?
I mean, fundamentally, these again become like, I think these are very clearly only software engineering matters, not programming matters, right? It only matters that you have control if you are trying to change it, right? If it already exists, but you never need to touch it again, who cares, right? And so the lack of control in either case is about how efficient is it to make changes and how risky is it to roll out those changes, right? And so you have to measure the cost of it being out of intellectual control by a change in productivity, which, hot take, we can't measure in the first place. So I don't think you're actually ever going to be able to measure this, not in a highly believable fashion.
Now getting into the really hard-hitting technical questions. Is there a backstory behind the flamingo, which is on the SWE book, and I can see the puppet on stage now?
Yep.
Yes, the shirt.
And the shirt. It's a blue flamingo print. So the O'Reilly doesn't give authors any input apparently in the animal that shows up on the book cover. So the first thing that I knew about like what was going on the book cover was, here's your book cover, flamingo. It's like, well, you know what? That could be worse. And then for book launch day, a bunch of my colleagues and my wife coordinated to buy every flamingo branded thing on Amazon. Like there was some budget here. And the idea was to like flamingo the ever-loving hell out of my desk for book launch. Unfortunately, that was March 2020. So that didn't happen, but one of my good friends and colleagues here, Matt Kulakundis, KFM, he lives in my building and he just had a small room closet in that space that was just full of flamingo stuff for like a year. And for my birthday, my wife organized getting me out of the apartment and getting Matt keys, and my apartment just got completely covered in flamingo stuff. So it is now my spirit animal. Like this is, yeah, there's flamingos in my life everywhere. Yeah. If you find cool flamingo things, yeah, send them to me. It's apparently how things are going now. So
There you go. Send Titus flamingos. Got it.
just don't tell my wife.
Next up, what are your thoughts on probes for testing changes as they roll out to production environments? Is this just a fancy statistical control? Might there be a future for fuzzing or property-based probes? Related, thoughts on emphasizing unit tests versus integration and cross-boundary tests?
Oh yeah. Ooh, there's way too much to unpack there. I did a tech talk for ACM on the software workflow fall 2023. It's on YouTube. So there's like an hour-long talk on all of this. Or otherwise, you can go back and watch the SWEdu sort of lessons and things. But yeah, like I think all of these are totally tied together. The probes for testing changes as you roll out to production. It's a whole mindset about the only evidence that your software is actually providing any value whatsoever is when it's in the hands of users, right? But doing all of your testing live in production is too risky and foolish to be useful, right? And so the way that we often look at like the software workflow, like autobiographically, is I have an idea and then I do this million series of steps of like bureaucracy and things getting in my way and it's so much process and then I'm done. Like, oh, that seems tedious, right? But if you look at it anti-chronologically, you have evidence of goodness in production, but that is too costly. What can you find that's predictive of goodness in production, but is less costly? Oh, that's canaries and gradual rollouts, right? Oh, but that's still costly because if I find a bug there, it takes me forever to I got to stop the release and you got to do all of the other things, right? And so what can I do that's predictive of passing canary, but cheaper, right? And you can look at every defect detection aspect of the software workflow as a series of proxies and filters, right? And then it becomes an optimization problem in terms of false positives and false negatives and what's the overall cost of running that intervention. But you also have to keep in mind that software only valuable when it's actually made it to users. So if you just add infinite latency to your workflow, you never actually can ship any new value, right? So we have to balance what is the time between submit and deploy. You have to balance what is the resource cost of running those set of tests. You have to balance false positives and false negatives rates, right? And all of these things, I think, start getting into the same space that you're sort of talking about. But like, there's way too much to unpack in that. I hope that helps a little bit. I don't know.
Let's see, next question. Does this distinction between real number qualities like performance and Boolean qualities, for example, there are no security bugs, affect how they're handled in testing and in your flowchart?
I don't think security bugs are Boolean quality, Brooks. But yeah, actually, I think that there's, I think most of the contiguous qualities, performance, et cetera, and Boolean qualities, functionality, right? There is a comparison to be made there in the functional quality, dichotomy. I think it's more often than not the case that a continuously valued thing is going to wind up being an equality attribute. I'd have to think about it. More often than not, I believe that. But.
See, next question. How do you feel about intellectual control being bolstered by socializing communal knowledge? Is that not real IC? Because as the team turns over, you're left with only unit tests from the flowchart and no IC.
I mean, no, I think the bolstered by socializing communal knowledge is the mission. There's a talk, or there's an essay. Jonathan can link to it. It's like coding in the dark. Kat Hicks did a research study on teams that have, better documentation about their practices and behaviors and details and how things work versus teams that don't. And like so much of research on what leads to team efficacy is about culture or documentation at root. Like all of the DORA research in the last 3 years, the most fundamental things are culture or documentation or both. And the coding in the dark paper actually, I think, explains why those are part and parcel, right? It's when you document how the things work and how your team behaves and that we care about learning together, right? That changes the nature of the team in a way that you're going to be more capable of having intellectual control. And like, yeah, intellectual control is not a property of a project, it's a property of the team, right? And so, yeah, you absolutely have to be socializing it. You have to be building those learning communities. You have to be focused on growing the people around you in order for it to be useful and successful. Or you have to hope that one very smart person has infinite availability and never retires. I don't recommend that.
See, next, what are your thoughts on code reviews and how much effort should go into them? In general, I'm not happy with the lack of questions in most code reviews that I've seen which have been approved. How important is it to dot the I's and cross the T's and hold people to that?
I think going to the point that I keep making here, code review is primarily good for holding ourselves accountable to a quality line. It is secondarily good for education and knowledge sharing amongst the team. And once in a while, you will find functional bugs. Most of the time, any functional bugs that you find in a code review are sometimes bugs like UB triggers or things like that, right? I forgot to take a lock on this mutex or something. It's relatively rare that you get a code review where like it just simply doesn't compute the thing it was supposed to, because we have tests, right? The unit tests are there to give you the statistical control evidence of basic functional correctness, right? And so if you're code reviewing with the intent of, I need to find the bugs in your code, man, you're probably doing it wrong. If you're code reviewing with the intent of, hey, what can I learn from you and what do you maybe need to learn based on what the code you've submitted looks like, right? That's a team growth, learning, education opportunity. And are we holding ourselves to the quality barrier or quality targets that we have agreed to for the quality attributes that we care about, right? And one of the great strengths of Google is historically, like readability is non-negotiable, right? And that's been one of the things that has really helped. And I know that there are teams where that has dwindled over the years. And, you know, that's, I think, largely because if you don't understand specifically what the role of that task is, and if you haven't agreed with the team about this is the, you know, level of nitpicking and quality that we're aiming for, then it just feels like I'm just getting up in your business for no good reason, right? With letting this one thing slip is not going to change the world. It's like, true, it's not going to change the world, but it does set a precedent. It does let people copy and paste. It does start the ball rolling on losing some quality. Right?
That's all we got in the Dory, but if there's any more questions in the GVC or in the room, happy to take those. We got about 13 more minutes.
Going once. Going twice.
Okay, cool. Well, then we'll wrap up. Thank you very much, Titus, for being here with us. This has really been great. We appreciate you having us or coming to see us, talk to us, answer all our questions. For all the rest of you in the audience, thank you for coming. We will have more Tech Talks announced on the software design mailing list, as well as other events and such, things like that. But otherwise, have a great rest of the week, everyone. And we'll talk to you all later.